Evening guys. So in previous classes we have discussed about adders, subtract, subtractors, right? So in today's class we are going to discuss about the concept called as multipliers. Okay. So do you guys have any ideas about multiplexer? Sorry, multipliers? Guys in the chat, okay? Big quick, okay. So we can discuss like more deep about multipliers, okay? Session we are going to discuss about this multiplier concept. So have you guys have any ideas on this topic? So, okay, I will understand. Okay, even here. So, as we know, today we are learning multipliers. So, first we need to understand fundamental concept of multipliers. Why we need multipliers? Why are they used in VLSI? What is its purpose? Like that, and what is the role acquired inside the uh, CPUs and GPUs? Okay, so so before this multiplier concept, I did I will give a brief introduction. Okay, so today we are moving into the next concept, right? So that is arithmetic circuit, which is also a arithmetic circuit. Okay, multipliers is also a arithmetic circuit, just like adders and subtractors. So multiplication is one of the most frequently used operation in processors, DSP systems, AI accelerators, image processing systems, and communication devices. So, what is the use of this multiplication? So in this session, we will study three important multipliers, okay? That are array multiplier, booth multiplier, Wallace tree multiplier, okay? So just remember these three multipliers: array multiplier, booth multiplier, and Wallace tree multiplier, okay? So just a minute. Yeah, okay. So I said we are going to discuss about three important multiplier architectures, right? What are the architectures? Array multiplier, booth multiplier, and Wallace tree multiplier, okay? So what are we going to learn on these multipliers? So we will understand their architecture, working principles, advantages, disadvantages, delay analysis, and also a real world applications, right? Okay. So yeah, jumping to the multipliers. So these are the things we are going to like learn inside this session. Okay. So uh, before starting the session, I have one question for you guys. Okay. So which operation do you think consumes more hardware resource, addition or multiplication or subtraction? So can you explain which operation perform more, like consumes more hardware resource? Guys in the chat, okay? Just if you don't know answer, just think and guess, okay? So which operation inside an hardware consumes more hardware resource. Option is addition or multiplication. Guys, answer guys. You need to cooperate to make this class interactive, okay? So just don't sit ideally. Just think, okay? If answer is addition, why? And if his answer is multiplication, why? That's the question for you guys. Start thinking, okay? So just answer it as soon as possible. Guys, if you don't know the answer, just say no sir, we have no idea. Then I will explain, okay? So ultimately the goal is to like you guys to make me to you guys to think like in the way am I possible, okay? So yeah, if you even if you don't know the answer, just put no sir, no, I have no idea. Okay. No one is listening, huh? No response from the chat. Yeah, okay. I can't wait any longer. So the answer is multiplication. Why multiplication? Because think you are multiplying something, okay? So if you are multiplying something, just think you are multiplying 11 into 11. Okay. How do you multiply 11 into 11? You will place 11 and 11 with the into mark question, right? And after that, under you are going to like first multiply 1 with 11 and write the answer plus and 1 with another one with 11. Like that you are going to multiply, right? So if you are going to do like that means just look into the thing what you are doing internally. After multiplying you will get the answer. Like you are multiplying uh, every terms of one number with all the terms of another number, right? So you are just multiplying one from second term with the 11, okay? After that another term with 11, like you are going to do two times here, right? So after doing two times, ultimately you are going to add that in the end, right? So what I'm trying to say is that you're not only multiplying here, you're also adding the answers of each term. So that's why multiplication, like uh, it takes more hardware resource. Okay. So inside multiplication, there will be several addition is going on. So that's why it makes complex. Okay. So just remember this answer. It will give you some ideas. Okay. So introduction. Let's us first understand why multipliers are important. Okay. Okay. Just imagine a processor executing 5 into 7 and 100 into 200. Okay. So inside your processor this operation occurs billions of times per second. Okay. So if your multiplication is slow, what will happen to the processor? The entire processor becomes slow, right? So therefore multiplier design is one of the most important optimization problems in VLSI. Okay. So just think like if your multipliers is very slow means your entire processor becomes slow. Ultimately, in your goal of in your VLSI is that to optimize this problem. Okay. So where are you going to use these multipliers? Sorry, processors in smartphones. AI chips, DSP processors, graphic cards, signal processing system, like etc. Right? So just remember the one point I'm going to say. Okay. So in modern AI chips, okay, modern AI chips spend more silicon area on multiplication than almost any other arithmetic operation. Okay, so inside your processor, right, there will be some chip, right? Just think, for example, uh, there will be some chips like in Samsung mobiles they have Snapdragon chip, right? Like that only in iPhone you have something like A19, A20 chips, right? So those are the chips like which have like appended with AI. Okay, so in that, like just think a random chip. Okay, so inside a random chip, the most there will be silicon area, right, where all your other designs were included. So in that silicon area, multiplication, like they spend that area only for the like main area for multiplication. Okay, so like other than there will be some space for other arithmetic operation also, but based on your multiplication, the processor speed and everything will be determined. Okay, I hope everyone got my point. Okay, so just look this. Okay, what are the need for multipliers? Like if you are designing a multiplier, what are the things you needed the most and why? Sorry. So multiplication forms the backbone of arithmetic processing. Okay, so whenever we perform A into B, okay, so the processor activates a multiplier hardware. Okay, I said right, in AI like processor there will be a chip like and inside that larger area like silicon area will be provided to this multiplication, right? So whenever your system receives like performs A into B, then processor tells that the chip to activate multiplier hardware. Okay, so what are that multiplier hardware? Like ALU operations, floating point units, and DSF filters. Okay, so and after that, sorry, this slide. Yeah, and the speed bottleneck. Okay, so suppose think we perform multiplication using repeated addition, right? Example like if you want to multiply 5 into 6, what is the answer of 5 into 6? 30, right? But what I'm trying to say is, instead of you multiplying the this answer like performing A into B, think you are performing this multiplication using repeated addition, means adding for 5 6 times, like 5 plus 5 plus 5 plus 5 plus 5. Ultimately we'll get the answer as 30, but instead of multiplication you are doing a repeated addition, right? So this will become extremely slow. Okay, so that's why uh, dedicated multiplier circuits are used. Okay, that is what the speed bottleneck, nothing but like naive. You have written something, right? Naive shift and add multipliers are too slow for G speed, means shift and add multipliers means like doing repeated addition. Okay, these are very uh, like less performance is very extremely low. So that's why you are using dedicated multipliers. Okay, so power trade-off. What to say for this? Like so, yeah, power trade-off means it's nothing but you are trading something with the power, means there are some things that are undergoing in inside your design, but to make it balance, you're trading that performance with the power. Okay, that is what the power trade-off means. Okay, just think, you're thinking like you're making a multiplier faster, right? So if you make that multiplier faster, like every parts need to work, right? So ultimately it increases the power consumption. So what happens if you're if you are going to decrease the power consumption means you're thinking like I'm going to reduce the performance. Okay, like I'm making it uh, slower, so like that power consumption will be slow. Like that, if you are thinking, your performance will ultimately reduce. So hence, when you're designing any where like if you are designing anything like multiplier addition, you must have a balance. Okay, it should be working in a particular speed, and your other operations like power consumption area should also be in a balance. Okay, then only you are going to become a good VLSI engineer. Have you heard about PPA? PPA is nothing but power performance area. Okay, this should be in balance mode, then only you can achieve this power trade-off. Okay, next, area cost. Okay, so think a 64-bit multiplier occupies a large silicon area. So the larger the multiplier, the more gates, the more transistors, the more chips are required, right? So for that purpose, you must think, if you are building a multiplier, it should be a cost efficient and area should be uh, as much as low as possible. Okay, so if you are doing in that way means ultimately your PP will be in a balanced mode. Okay, if you are going to next slide, applications of multipliers. Yeah, like I said, where you are going to use these multipliers inside CPU, ALU, DSP, AI accelerator, signal processing, etc. Right? So the CPU, whenever CPU perform automatic operation, multipliers are used. Like how these multipliers are used? By the help of processor. Processor tells that I have a multiplication operation, so I'm going to activate the multipliers. Okay, so like that, inside your CPUs, multipliers are used. So inside DSP, like this signal processing, multiplication is everywhere. Okay, for example, audio processing, video processing, filters, FFT, FIR, IIR, like that. Everywhere inside your DSP, multipliers are used. Okay, so like that also in AI accelerators and signal processing. In signal processing, these multipliers are used. So just a question: in which field uses the highest number of multipliers today? Do you guys have any idea on this topic? So the answer is AI accelerators. Okay. So AI accelerators is the field where you are going to use highest multipliers. Okay. So I'm just not going to tell why, because if I say everything means, don't get like that eagerness to study. Okay. So just move and search like what are the things inside this AI accelerators, right? So if I want to become a good VLS engineer means you should know everything, okay? So just check what this AI accelerator is about and what does it do and why we need these AI accelerators, okay? So I said right, for multiplication you should know fundamentals, right? So so before implementing hardware multipliers, we must understand binary multiplication, right? So take an example like multiplying some numbers 1 0 and multiplied with 0 1, okay, or 1 1. What is the answer you are going to get for that? Like we should do in binary format, right? So if you multiply this, just like in addition, everything inside the multiplication is also same, okay? So if you take 1 0 multiply with 1 1, okay, first you need to multiply 1 0 with single digit 1, then your answer is going to be 10, right? Like means 1 0 plus same answer 1 0. So after that you are going to addition, right? So what is the answer you are going to get? 0 1 1, 0 1 1, right? So your answer will become 1 1 0. So what is the decimal value of 1 1 0? 6, right? So if you are multiplying, what is the value of 1 0? 2. 1 1 means 3 in decimal value, right? So ultimately you are multiplying 2 into 3 means you are going to get 6 as answer, right? So in binary multiplication also you will get the same answer. Here, I have taken another example, okay? What is the decimal value of this 1 1 1 0 1 1 11, right? And 1 1 0 1 13. If you are going to multiply this answer, first you need to multiply like the first term is called as multiplicand, okay? Multiplicand. And the second term is called as multiplier, okay? So from multiplier, like the first digit is multiplied to every multiplicand, and after that every digit from multiplier is multiplied with multiplicand, right? So that's how you are going to get this answer. So just think what I say, okay? So what is the answer if you are going to multiply this with 1 with this, okay? Your answer will get same, right? 1 0 1 1, 0 with this number 0 0 0, and 1 with this number same number, and 1 with this number same, right? Like this you are going to shift, right? Like this shift, you need to shift this, right? You need to shift that, right? Like you are writing plus here plus 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 plus, like that you are going to write, okay? So just observe this example. This is word is there, right? See here, you can see 1 into 1 0 1 1, right? So this each row is called as partial product, okay? So just remember this word partial product. It's like it's required to know like what is the partial product means, okay? So partial, this each row that you have multiplied with multiplier and one multiplier, okay, that is called as partial product, okay? So there are like there are important concepts in multiplier architecture, okay? So that contains two stages. What are the two stages? Stage 1, partial product generation, and second stage, partial product addition. Okay, so just remember these two steps: partial product generation, partial partial product addition. Okay, so now we have generated the partial product, right? So this is what called as the single row. This row is called as partial product. How many partial products are there? Four. Okay, so after you are like generating a partial product, then the second step is partial product addition. Means you are going need to add this, right? So if you are going to add this, then you will get the answer. How? One will be there, like one, right? So 1 0. If you add 1 0, then what is the value you are going to get? 1 0 0 1. The answer is 1. Then 1 0 1 1. Now you have three ones, right? Three ones. So what are you going to do with three ones? Means the output, like if you add 1 1 1, what is the answer? 3, right? So here you going to write 3 in a binary format, double one, right? So writing 1 year and carrying 1 year. Okay, now just add this. Okay, 0 1 1. Answer is 1, right? But for this row you got double one, so you have borrowed 1 year, sorry, carried 1 year, right? So your option will become now you have two ones, right? 0 0 1, two ones. So the one which is you have carried will becomes like two ones, right? So if you add 2 means you will get answer as 10. Okay, so that's why you have 0 here and 1 carry. And for same that also, 1 1 2 ones, 0 1 carry. Now 1 is there and you only have 1 year. 1 plus 1, 10. That's your 10 year. Okay, so this is how you are going to add. So I hope everyone got what is partial product addition, generation and partial product addition. Okay, like this is the generation matrix what I explained. Okay, so for 4-bit multiplier means 4-bit input. Like I said one example, right? So we are going to multiply like this only, right? Just like that. Just how you added everything, right? Like 1101 multiplied with 1011, right? So you multiply like this. So you're multiplying bit 0 of second element with the first element and you will get the answer here. And first bit 0 with first element. Like means what I'm trying to explain is, look here. You have multiplied this first one with every element, right? With this every element, then you got this output. That is what you are storing here. First bit is multiplied with every element, then you are getting this line. And second element with every element this. Third with this. Fourth with this. This is how you are going to create matrix. This is the form of matrix format. Okay. So what are the hardware challenges inside the multiplication? Okay. Now let us understand why multiply design is becomes like difficult. Okay. So challenge one is delay. So why delay occurs? Just think, okay, why delay occurs? Just to say in a simple word, because of addition. I said right, inside addition, you're it's going to occur like carry and propagate, right? So you're going to propagate that carry that you have generated. That time the delay is going to come, okay? Second area, sorry, second challenge, area. Okay, area complexity means more bits require more gates, right? And more adders and more wires. So that's why more complexity. power. So just think you're computing some bits, right? So there will be something like if you are multiplying at a time, there will be many switch active. Why? Because you are multiplying, and at a time you are somewhat additioning. For that addition, there should be some full adders active at a time, right? Like full total number of gates should be active. Like many number of gates should be active for uh, complete that progress. So the power will be used more, right? So that's why power dissipation will be more. Next thing is carry propagation. Okay, just like I said, right? You're propagating that carry delay that's going to produce, right? So that carry should travel from the area that you have generated to the until it's like it's dissolved inside your addition. Okay, so that's why propagation delay occurs. So okay, so this is the amount of a like silicon area you are going to use. Okay, so this is measured inside a like this unit. Okay, like just remember this unit and delay. Just like these are the some interview questions that they are going to ask. Okay, so mu square. Okay, unit is like mu square, and after that delay is like its unit is in form of PSNS, and power is measured in milliwatt. Okay, so these are the some things you should remember, like what are the performance matrices that area, delay, and power you are going to use. Okay, like how, like area is nothing but number of logic gates into gate area. Okay, yeah, these are the some interview questions you should remember. Okay, like what are the units and what are they, how you are going to define them. Okay, yeah, okay guys, I think this is enough for this class. Okay, so tomorrow I'm going to explain array multiplier, boot multiplier, and wall create multiplier. Okay, so I hope everyone got the like basis of multipliers, why we need, what is the use of that. Okay, so yeah, guys, thank you for the attending class. You may leave now. Okay.